Support vector machines, or SVMs, are powerful tools in machine learning. They classify data with impressive accuracy. SVMs find the best line or hyperplane to separate classes. Think of separating apples and oranges. The margin acts as a buffer zone. SVMs handle high-dimensional data and prevent overfitting. They are invaluable for various applications. Imagine a classroom with students scattered around, some wearing blue shirts and others red. The teacher, representing an SVM, wants to divide the room so that students with the same shirt color are grouped. This dividing line is the decision boundary. The SVM's goal is not just to draw any line, but to find the one that maximizes the distance between the boundary and the closest students from each group. This distance is called the margin. A larger margin implies a more confident and generalized classification. The decision boundary is determined by a subset of the data points called support vectors, which lie closest to the boundary. These points are crucial as they directly impact the position and orientation of the decision boundary. In essence, SVMs aim to find the optimal decision boundary that maximizes the margin, ensuring a clear separation between different categories and a more robust classification model. Support vectors are the key players in an SVM model. They are the data points that lie closest to the decision boundary. Think of them as the influencers that determine the position of the dividing line. The margin, on the other hand, is the empty space between the decision boundary and the support vectors. It represents the SVM's confidence in its classification. A wider margin indicates a more confident and generalized model. Imagine a street separating two rows of houses. The support vectors would be the houses closest to the street, and the margin would be the width of the street itself. A wider street provides more separation and reduces the chances of houses from opposite sides being mistaken as belonging to the same side. SVMs aim to maximize this margin while minimizing classification errors. This ensures a more robust and accurate model that can generalize well to unseen data. Section 4, kernels, the key to nonlinearity. In real-world scenarios, data is rarely linearly separable. Imagine trying to separate a mixture of salt and pepper with a single straight line. It's practically impossible. This is where kernels come into play. Kernels in SVMs are like special lenses that allow us to view our data in a higher dimensional space. By projecting the data into this new space, we can often find a linear separation that wasn't apparent in the original dimensions. Think of it like drawing on a flat piece of paper versus a crumpled one. A straight line on the flat paper might become curved when the paper is crumpled. Kernels provide a way to crumple our data space, allowing us to find non-linear decision boundaries. Different kernel functions exist, each with its own way of transforming the data. Choosing the right kernel depends on the specific dataset and problem at hand. Section 5, advantages and limitations of SVMs. SVMs are effective in high-dimensional spaces and robust to overfitting. The kernel trick allows efficient handling of non-linear data. However, they can be computationally intensive and memory-hungry. Despite these, SVMs are powerful for complex datasets.